Hello everybody, my name is Ariyani Kumala Sari. My last digit number is 013. Here, I will explain about limit of function. So, let's review our intuitions on what a limit even is. So, let me show some axes here. So, let's say this is my y-axis. So, try to see a vertical. So, right over there is my y-axis. And then let's say this is my x-axis. I'll focus on the first quadrant. On top, I didn't have to. So, this right over here is my x-axis. And then, let us show a function. So, my function looks something like that. It could look like anything, but it seems suitable. So, this is a function y is equal to f of x. And just for conceptual understanding, it needs to be defined at the point. I didn't have to do this. You can find the limit as a push a point where the function is defined, and it becomes much more interesting. This is when you start to understand why a limit might be relevant where a function is not defined at some point. So, as I'm showing it, this function is not defined when x equals c. Now we talk about a limit. Just f of x approaches as x approaches c. Let's think about that. When x is a bit lower than c, f of x for the functions we just draw is right over here. That's what f of x is going to be equal. Y is equal to f of x. When x gets closer, our f of x is suitable over there. When x gets even more intimate, maybe almost at C, but not quite at C. Our x is right over here. And the way we see it, our f of x seems to be as x gets closer and closer to C, it looks like our f of x is getting more relative to some value. It's getting closer and closer to some value right over there. And that was only the case when x was getting closer to c from the left. From letters of x less than c. But what happens as we get closer and closer to c from values of x that are greater than c? Well, when x is over here, f of x is right over here, and that's f of x is right over there. When x is slightly closer to c, f of x is suitable. X is somewhat larger than c, our f of x is suitable, and you see once again it seems to be approaching that some value. And we call that value that f of x appears to be coming as x approaches c. We call that value L or the limit. And so the way we would then denote it is we would call that limit. We don't always have to call it L, but it's called the limit. And we will write it mathematically, we would say limit of f of x. And this is an excellent conceptually. And we will write that mathematically, we would say the limit f of x as approaches c is equal f. And this is an excellent conceptual understanding of limit. And it will take your part. And you are ready to progress and start thinking about taking final limits. But this isn't a very mathematically rigorous definition of limits, and so this set us up for the intuitions. Okay, let's devise a mathematically rigorous definitions for what this statement means. The statement that the limit of x as a approaches c equals f. So let's say this means that you can get f of x as close as you want, by getting x sufficiently close to c. So another way of saying this is if you tell me, hey, how to get my f of x to be within 0.5 of this limit, you're telling me that if this limit is true, you should be able to hand me a value around c that if x is within that range, the f of x will be as close to L as I decide. So let me show that how to make it a little bit clearer. And I'm going to zoom in. I'll show another term. So let's say that is my y-axis, and I'm going to zoom in. I will show a slightly different functions. So we can focus on what's happening around here. The range is around C, and the range is around F. So this x. This range over here is y. Let's say that this is C, and let's zoom in on our functions. So let's say our function is doing something like, let's say it is something like, let's see, we want it to be defined C. And just for that it could be, you can always find a limit even where it is defined. But let's say our functions look something like that. It can even have a little thing in the way I drew it, so it looks something like this. It's undefined when x is equal to c. So this is the point where there is a point. It is undefined when x is equal to c, and it even has a little thing in it, just like that. And we want to prove that the limit of x, and let me clarify, is the graph of y equal to f of a. We want to understand what this definition means if we claim that the limit of x at x and versus c is L. So as I told you, we get the case already. We already get the case that this right over here is L. Now let's going over limit properties, and you can apply this age properties of limits to every property. Some simple limits. Essentially, how you can use these properties is to break down slightly more complicated limits into smaller pieces that are easier to evaluate, and that can be evaluated using these 8 properties. Then apply them to a smaller pieces of that limit before you can, put it all back together to find the full limit. So I'm going first to show you on these 8 properties, and then I will go into a couple of examples to show you exactly how to apply just 8 properties to evaluate limits. So let's go ahead and get into it. So this first property here, limit as x tends to any of some constant c equals just this constant. So essentially, how this means is if you are taking the limit as your variable just to any number of just some constant number, the result will just become constant. Essentially, limit 1 have any effect on that constant. This one is straightforward on that constant. This one is straightforward. The second property essentially says if you have the limit as your variable goes to some number of just your variable, it will give you that number. So this is self-explanatory. Essentially, all it's saying is as x gets close to a, what number will x approach? Well, it tells you here that x is going towards a. So therefore, x is going to get close to is the same kind of idea. When this first property, if our variable x is getting close to some number that is constant c, it's not impacted by c is going to be c no matter what x is. So this limit x is getting close to a and c is just going to remain c. These first 2 properties here are essentially the condition that any limit you are trying to evaluate will be broken down into these 2 properties. So these 2 properties will usually be the last 2 you apply. You will work your way, back from there, the rest of the 8 properties, so the next 6 that I'll get into will help you take and limit and deconstruct it down into these 2 properties. Then you can apply these 2 properties and the variant. So now, this third property here basically says that a constant being multiplied by an entire function can essentially just be pulled out of the limit. So if we have some limit as x is going of some constant times a bunch of other stuff, the constant multiplied by everything else can just be pulled out of the limit. And essentially, it allows you to find the limit as x equals a of all this other stuff in there. And then once you figure out what that limit is, you can multiply it by your constant c, after you have found this simple limit. So now, this for property here, basically, say we have the limit of 2 things being added or subtracted, it will be plus or minus. We can find the limit of each of these just individually and then add or subtract the result. So basically, allows you to break down. If you have a limit that is the sum or difference of a bunch of different terms or a bunch of similar functions, you can break it up into a bunch of smaller limits and then add or subtract the result from each of those individual limits once you found those individuals. So again, it's just how you break it down into smaller pieces of them are a little bit easier to deal with. So this fifth property is the same idea as the fourth property. And instead of adding or subtracting, we have multiplication here. So if we have a limit as x plus the sum of two functions being multiplied together, we can find the limit as x gets to each of those things individually and then multiply the result of each of those limits after the fact. So this could be used, if we ever have some functions multiplied by a bunch of other stuff, maybe you have something that you could factor up or factor some polynomial or something like that. With a couple of different factors being multiplied together, you can find each of those limits individually and then multiply the result instead of having to deal with all of the jumble up together. And then, since it works with multiplication, the same kind of idea also works with divisions. Suppose you have some fraction that you are taking the limit of. In that case, you can take the limit of the numerator and the limit of the denominator individually and then put them back into a fraction of each of those limits after you found the limit of the top and the limit of the bottom separately. You need to remember what is what help. So if this limit is 0, this won't work. If you get the limits as x plus 2a of g of x equals to 0, then this will cause you to divide by 0, which you can do. So as long as you are making sure that taking the limit of the bottom of your fraction doesn't give you 0, this would be a good way to simplify things for you, and then you could keep going from there using the other limit properties. If taking the limit as x squared and of g of x equals 0, you have to do something else to help simplify this limit. Maybe you can employ the limit using these limit properties. You might have to do something else. For example, if the limit of not also gave you 0, so that you got 0 over 0, it could potentially be a case where you could apply a hospital rule, for example, resulting yeah, I think this is now. Okay. The point is, if this limit here gives you 0, you will have to do some other method. There's a handful of other things you could do, which maybe I'll feel on just at some point in the future, so you will then be able to apply these properties to implement that limit. So then this lecture of this here tell you how to deal with powers and groups within limits. So if you have the limits of something being raised to a power, you can instead take the limit of whatever was inside that power and then raise the result to the power. So it's essentially just pulling almost like pulling power of the limit. The limit was stuck inside the power first, and then once you have dealt with that and figured out what that is, then you can do the whole thing up to that power and then lastly wire. So you have to deal with groups within limit. So if you have the limit of something that's object within some root, this could be square, root 2, root 4, root, so on and so on. You can essentially take the limit of whatever was inside the root and then take the root of the whole thing afterwards. So that works out the limit properties. Let's say that f of x equals x squared plus x minus 6 over x minus 2. We are curious about what the limit of f of x plus x over 2 is equal to. You might want to make right when you see something like this is to see what happens. This f of 2 is not always be the limit, even if we find it. It's a good place to start to see something reasonable will go up. So looking at it this way, if we evaluate f of 2 on our numerator, we will get 2 squared plus 2 minus 6. So that will be 4 plus 2, which is 6 minus 6. You're going to get 0 in the numerator, and you're going to get 0 in the denominator. So we jump up the function is not defined. So not defined and x is equal to 2. Not defined. So there's no simple thing here. There. Even if this is equal, if it were a continuous function, then actually the limit will be whatever the function is. And it doesn't necessarily mean the case. We see clearly that the function is not defined here. So let's see if we can simplify this. And we'll also try to graph it in somewhere. So one thing that might have jumped out at your head is that you might want to factor this expression out. So if you want to rewrite this, we could rewrite the full expression and discuss to your algorithm. Two numbers whose product is negative 6. Whose sum is positive 3. Well, they could be positive 3 and negative 2. So this could be x plus 3 times x minus 2 over x minus 2 as long as x doesn't equal 2. These two things will cancel. So we could say this equals x plus 3 pull out x except for x equals 2. As long as x doesn't equal 2. So that's another way of looking at it. Another way we could rewrite our f of x. Look at change the color. We could rewrite f of x is the same function. F of x equals x plus 3 when x doesn't not equal 2. And we could even say it's undefined when x is equal to 2. So given this definition, it becomes much clearer how we can graph f of x. So let's try to do it. So it's not anywhere near being a straight line. It is much better. So let's call this UAS. I'll call it y equals f of x. And then let's over here let me make a horizontal line like that. And this is my x-axis. To define this way, f of x equals x plus 3. So if this is 1, 2, 3, we have y and the side is 3, and then the slope is 1. Slope is 1, but it's defined for all x except that x equals 2. So this is equal to 1 and x is equal to 2. So when x is equal to 2, it is undefined. So let me make sure I get so it's defined right over there. It's undefined right over there. So this is what f of x looks like. Now, given this, let's try to answer our question. What is the limit of f of x as x equals 2? Well, we can look at this graphically. This is 2 from lower close and 2. Just right over here is that x equals 2. If we get to maybe, let's say, this is 0.7, we see that our f of x is right over there. If when we get to 0.9, our f of x is right over there, so it seems to be approaching this value right over there. Similarly, as we first do from fellows greater, then if we are I don't know, this will be like 2.5, our f of x is right over there. If we get closer to 2, our f of x is right over there. And once again, we look like we are pushing this value. And another way of thinking about is if we write this line from the positive direction. We seem to be pushing this value for f of x. If we write this line from the negative direction from values less than 2, we seem to be approaching this value right over here. And this is essentially the value of x was there if we set it at equal to 2. So this we essentially see this value right over here is equal to 5. If we look at it eventually, if we just grab a line with 0, 1 with a y-intercept of 3, this value over here is 5. And we can also try to do this numerically. So let's try to do that. So if this is our function's definitions, obviously then shall they go to our original definition, we try to as x is closer to 2, so let's try to less than 2. So 1.99, this is not obvious. 1.99 plus 3, well, this gets equal to 4. If I have more nice, here and go closer to 2 with get closer to 5. If we approach 2 from the positive direction, and once again we are getting closer and closer to 5 from the positive directions, and we are closer to 2 with closer to 5. So when we look at it numerically, or we look at it graphically, it looks pretty clear that the limit here is going to be equal to 5. So let's see if we can find the limit of f(x) across negative 1 of 6 point. The first thing that might jump out at you is this upper here. This expression can be used to define the graph of parabola. And when you think about this, I'm not doing pictures from here about what would look like this. This would be an upward opening parabola looks like something like this. It's, it is visually continuous. You don't see any jumps or gravity. And generally, a quadratic like this will define it for all values of x for all real numbers, and it will be continuous for all real numbers. Or something is constant for all real numbers. But so is a versus some actual number, the limit will be the same as just equating the expressions at that exact number. So what am I saying? I'm just going to tell it another way. Some function is continuous at some x value at x equals a if, and only if I will write it as if, or if and only if the limit as x versus f of x is equal to f of a. So I didn't do a reverse from here, but it's conceptually not a big jump state. This is just a sliver quadratic frame over here. It's defined for all real numbers and continuous for all real numbers. And so we know that these expressions could define constant functions. So that means that the limit as x approaches a for these expressions is same as equating these expressions at a. In this case, our a is negative 1. So all I have to do is consider that is this f negative 1. This will be 6 times negative 1 squared, 5 times negative, and 1 minus 1. So that's just 1. This is negative 1. So it's 6 minus 5 minus 5 minus 1 equal to 0. And we are done with is equal to 0. So it is only problem. The next if we plug in 7, notice that we get 7 plus 2, which is 9. The square root of 9 being 3 minus 3, and we'll get 0 on top. Again, if we plug 7 in the bottom, we'll actually get 0. The thing to notice here is that we have a square root and there are 2 terms in the numerator. The common trick when you have radicals is to multiply by the conjugate. And again, the conjugate is basically if you have something plus or minus something, the conjugate of it is the same thing except for the sign is reversed. So in this case, instead being a minus, I'm going to multiply the top and bottom by the conjugate of the numerator. So here will go minus 3, and I will bear that by the conjugate, which is radical x plus 2 plus 3. So yes, the sign in the middle is the one that has changed here. I've got my x minus 7 on the bottom. If you multiply the top by something, you have to bear the base by that same thing. And now we will simply be the part where we reproduce the conjugate. I'm going to multiply the denominator at all. It's just an extra one. So the square root of x plus 2 times the square root of x plus 2. The radicals will cancel out, leaving you with positive x plus 2. Notice that one on the outside we'll get the 3 times radical x plus 2, but on the inside we're getting a negative 3 squared x plus 2, and just will cancel out. That's the point of using the conjugate. And then I'm left with the negative 3 times the plus 3 minus 9. So if you just see all this, you know, on a separate piece of paper, work it out and convince yourself that you will get this in the numerator. Again, I must do something on the bottom, x minus 0. I'm going to call x plus 2 plus 3. I'm still hanging out. Okay, I'm doing some algorithm. It's some play. Plus 2 minus 9 in the that gives me x minus 7, and then this is why probably I didn't cancel out by the method, or actually multiply all the if here and I multiply it by the conjugate, all the problems. So if it that is things what happens out, I have radical x plus 2 plus 3 left over. I can cancel out the x minus 7 and x minus 7. Of course, you can think about times 1 left on top. And now I'm going to plug my 7 in. I'll get 1 over the threshold of 9, which is 3 plus 3, which is 6. And that'll be my answer to me. When you see the radical at the beginning of the problem, try multiply by the conjugate. Furthermore, if you do it to the top, you have got to do it to the bottom. Just simply start where there is the conjugate. With the other problem, you still have something that will cancel out for you, just like that. X minus 7 did in this case. Okay? Okay. We now have much experience taking limit of functions. If I'm taking the limit of f of x, we're going to think about what f of x grows as x approaches some value a, which will be equal to some limit. What we have done until now is where a is a finite value. When you look at the graph of the functions right over here, you see something interesting happens. It's getting larger and larger. Functions at its closer to 2. We have a horizontal asymptote at y equals 2. Similarly, as x gets more negative, we have our horizontal asymptote at y equals 2. We can use some notation to think about what the graph is approaching as x gets much more significant or as x gets smaller and smaller. And the answer is there are limits at infinity. Limit at infinity. So if we want to think about what is the graph is and what is the function is approaching as x gets larger and larger, we can think about the limit of f of x as x approaches positive infinity to make the relation. And which if you have formal definitions from the future videos, we may do that. But it's this idea that x gets larger and larger and larger, it's like our function is approaching some finite value. And we have a horizontal asymptote there. And in this situation, it seems like it is coming to value 2. And for the particular functions, limit of f of x as x approaches negatively infinity also looks like it is approaching 2. Since sometimes going to do with different, you could have a situations and another function. So let me show a horizontal asymptote right over here. You could imagine a process that looks like this. So let me do it like this. Maybe it does something like this and it comes down. And it does something like this. Here, our limit as x approaches infinity is still 2. But our limit as x approaches negative infinity right over here would be negative 2. And of course, there are many situations where your approach infinity or negative infinity and your current coming for some infinity value. You didn't have a horizontal asymptote. But these videos, both when it's the very familiar with you with these notations. And limits at infinity or limits at negative infinity have a different formal definitions than some of the limitations we've looked at in the past where we are approaching a finite value. But into deeply limiting that these are indefinite. So we have f of x equaling for x to the fifth x minus 3x squared plus 3 then over 6x to the fifth minus 100x squared minus everything about limit of x as x approaches infinity. And there is no way that you could do this. You could plug in larger and larger numbers for x and see if it is coming to some value. Or you could reason through this, and then when I'm talking about reasoning through this, thinking about behavior of this numerator and denominator as x gets very, very, very large. And when I'm talking about it, what I'm saying is as x gets very, very large, let's focus on the numerator. As x gets very, very large, let's turn right over here at the numerator. 4x to the fifth is going to become much, much more significant than any of these other things. Something squaring is large, but something being raised to the fifth power gets raised much, much faster. Similarly, in the denominator, this term term right over here. The highest degree term with 6x to the fifth is going to grow much faster than any of these other terms. Even though this has 100 as coefficients or negative 100 as a coefficients, it might grow much quicker when you take something to the fifth over than x squared. So as x gets very large, this thing will approximate 4x to the fifth over 6x to the fifth, or colossal x, or as x approaches infinity. Now, what could this be simply? X to the fifth divided by x to the fifth. Now I'm going to approach it, so you can take all these canceling out, so you are left with two terms. So the limit of x as x approaches infinity as x gets larger and larger and larger, of these other terms don't matter much. So it will come to terms. It's going to approach two terms. Now look at the graph and see if that makes sense. We are saying that we have a horizontal asymptote at y equal to two terms. So look at the graph. Okay, look at the graph. So right here is the graph. We put it from alpha, and we see in the this x is large and large of f of x seems to be approaching this value that looks right at around 2 terms. So we have a horizontal asymptote right over here. Let me draw that a little bit neater. We have a plane asymptote right at 2 terms. So let me draw it as neatly as I can. So it's right over here as y is equal to 2 terms. The limit as x gets large as it approaches infinity, as y is getting closer and closer to 2 terms. And when we look at the graph here, it seems like the same thing is happening from bottom direction when x approaches negative infinity. So the limit of f of x as x approaches negative infinity also looks like it's 2 terms. This is some logic. When this becomes a very negative number, as it will focus farther to the left of the number line. The only terms that are going to matter are the 4x to the fifth and the 6x to the fifth. So this is true for very large x. It's also true for every negative x. As x approaches negative infinity, it is also true. And then the x to the fifth over the x to the fifth will cancel. There are dominant terms, and we are going to get it equally to terms. And once again, you see that in the graph here. We have a horizontal asymptote at y that is equal to 2 terms. We take the limit of f of x as x approaches infinity, we get to terms. And the limit of x as x approaches negative infinity is 2 terms. So in general, whenever you do this, you have to think about what terms will dominate the race and focus functions. Okay? So let's see if we can find the limit as x approaches the negative infinity of the square root of 4x, the 4 minus x over 2x squared plus 3. Like always, this video can see if we can find limits. Whenever we're trying to find limits at either positive or negative infinity or rational expression like this, it's helpful to look at, well, what's the highest degree term in the numerator and the denominator? Let me divide the numerator and the denominator by the highest degree, by x at the degree. Because if we do that, we are going to end up with some constants and other things that will go to 0 as we approach positive or negative infinity, and so we are going to find this limit. So I'm talking about now let's define the numerator by over a squared and divide the denominator by 1 over x. You might be saying, wait, I see an x to the fourth here. That's a higher limit. But remember, it's under the radical here. So, if you want to look at it at a very high level, you are saying, okay, well, it's the fourth, but it's under, you're going to take the square root of this entire expression. So you could view this as the second degree term. So the highest degree is second degree. So let's divide the numerator and the denominator by a squared. And if we do that, I think this is going to be the same thing as So this is going to be the limit as x approaches negative infinity of. So let me do a little bit of an insight there. So if I have 1 over x squared, let me write it. Let me show it. Let me 1 over x squared times the square root of 4x, the 4x minus x, as we have the numerator here, is equal to, and is it the same thing as 1 over the square root of x to the fourth times the square root of 4x to the fourth minus x. And so this is equal to the square root of 4x to the 4x minus x over x4 to the 4, which is equal to the square root of, and all I did is apply the radical in here. You can view this as square root of all this divided by the square root of this, which is equal to, using our exponent rules, the square root of 4x to the 4 minus x over x to the 4, and then this is the same thing as 4 minus x over x to the 4 is 1 over x to the third. So this numerator will be square root of 4 minus 1x to the third power, and then the denominator will be equal to, well, unify 2x squared by x. You're just going to be left with 2, and then 3 divided by x squared will be 3 over x squared. Now let's think about the limit as we approach negative infinity. As we approach negative infinity, this is going to become 0. 1 divided by this, then becoming more and more negative. Then magnitude is getting larger. So this is going to approach 0. This over here is also going to be approaching 0. We're dividing by larger and larger values, and so this will result in the square root of 4. The principal source of 4 over 2, which is the same thing as 2 over 2, which is equal to 1. And we are done. Let's say that of x equals x over the square root of x squared plus 1. And I want to check about the limit of x as x versus positive infinity, and the limit of x as x versus negative infinity. So let's think what these are going to be. Well, again, I am not doing this is an ultra rigorous way, but I'm more intuitive is to think about why this not just approximately equals as we get larger and larger x. This is if we get very positive x equals what did I say? Okay. Well, once again, I'm not doing this. This is if we get very positive x infinity direction or negative. So all these things that are very larger as we approach positive infinity or negative infinity. Well, in the numerator, we only have one term. We have this x term, but in the denominator, we have two terms under the radical here. And x get larger and larger, either in the positive or the negative direction. This is square term will denominate this one. But this will have a negative square plus 1. This is square term will dictate the value of the denominator. So this will be approximately equal to x over the square root of x squared. This term over here, the 1 doesn't matter so much when we get very large x. And right over here is over the square root of x squared, or is over the principal source of x squared, will equal x squared. If I square something and then take the primary code, remember the principal root is to the positive square root of something, then I'm instantly taking the absolute value of x. It will be equal to 8 over the total value of x for x approaches infinity, or for x approaches negative infinity. So another way to say this, another way to list this limit is as we approach infinity this limit, we can repeat it as the limit is going to be equal to the limit as x approaches infinity of x over the absolute value of x. Now, for positive x, the total value of x will be x. This is going to be 8 divided by 8. So this is just going to be 1. Similarly, right over here, taking the limit as we go to negative infinity, this will be the limit of x over the absolute value of x as x equals negative infinity. And remember, the only reason I was able to make this statement is that f of x and this string right over here become a very similar, or you can say converge to each other as x gets very or large, or x gets very image. The negative expression, the absolute x will be positive. This is going to be negative, and we are just going to be negative one. You see, we can try to drag our function. So let's try today. So let's say this is my y-axis and this is x-axis. And we see that we have two horizontal asymptotes. We have one horizontal asymptote and y is equals to 1. So let's say this over here y equals 1. So we show that lines as the line. We are going to approach this thing. And then we have another horizontal asymptote at y equal to negative. So that might be right over there. Y is equal to negative 1. And if we want to put at least 1 point, we will think about what f of 0 equals. So f of 0 will equal 0 over the square root of 0 plus 1, or 0 squared plus 1. Well, that's always going to be equal to 0. So we have this point right over here, and we know that x is the process infinite. We are approaching this blue horizontal symbol, so it might look something like this. Okay, let me do it a little bit different. There it goes. See, so it might look something like this. It might look something like this. We get closer and closer. It's get larger and larger. And then, like this. We get closer and closer to this asymptote as it's across negative infinity. So right over there is equal to f of x, and you can verify this by taking the calculator, trying to put more points, or using some brain calculator or something. But anyway, I just want to tackle another situation where we are approaching infinity or negative infinity and trying to determine the value of the horizontal asymptote. And remember, the k is the same. What terms dominate as x becomes very approaching positive infinity or negative infinity? To say, well, what is the functions going to come? And this horizontal asymptote will come in the positive direction and this one in the negative. What of 0 equals? So f of 0 will equal 0 over the square root of 0 plus 1, or 0 squared plus 1. Well, that's always going to be equal to 0. So we have this point right over here, and we know that x is the process infinite. We are approaching this blue horizontal symbol, so it might look something like this. Okay, let me do it a little bit different. There it goes. See, so it might look something like this. It might look something like this. We get closer and closer. Get larger and larger. And then, like this. We get closer and closer to this asymptote as it's across negative infinity. So right over there is equal to f of x, and you can verify this by taking the calculator, trying to put more points, or using some brain calculator or something. But anyway, I just want to tackle another situation where we are approaching infinity or negative infinity and trying to determine the value of the horizontal asymptote. And remember, the k is the same. What terms dominate as x becomes very approaching positive infinity or negative infinity? To say, well, what is the functions going to come? And this horizontal asymptote will come in the positive direction and this one in the negative. So I think we didn't have something about some real life things are this. Okay, so do you know how limits are used or applied to daily life or applied to real world problems? Real life limits are used whenever you have some real world applications to pursue steady state solutions. Right? Does the concept of infinity have any practical applications? Okay, great. We will learn one by steps. For example, a chemical reaction in bigger stars with two chemicals forming a new compound over time. The amount of the new compound is the limit of functions as time versus infinity. Similarly, simple structure and an isotope in warm water and measure temperature with time. In this case, temperature evenly approaches the room temperature where the glass is stored. Measuring the temperature is limited again as the time of proceeding. Limits are also used as real-time approximations to calculate daily factors. It is challenging to calculate the results of complicated motions in real-life situations. So, to make calculations, engineers will approximate functions using minor difference in the process and then try and calculate the functions derivative by having smaller and smaller spacing in the functions simple intervals. For example, when deciding the engine of a new car, an engineer might model the gasoline stroke the car's engine with small bricks called mesh since the inch geometry is too complicated. And recently with simple functions such as polynomials, these approximations always use things. I know what you're thinking. Of course it has. Okay, this is a second one. Just the concept of infinity of any practical applications. When you're thinking, of course it has. For example, it can tell you how many times you can go around a cycle, but it's noisy. You think that or the word where the analog before infinite loops have been reached. Infinity in what sense is infinity are crucial for some fundamental stable counts, which is helpful in real-world applications. We're not talking about infinity limits, we're talking about how numbers behave as they get larger. In this case of series and we add more and more terms. Let's take the version x plus a, where a is more constant and we take a limit as x, if we will find the functions first too. At first, you might look at this and say, so what? Just say, since x becomes large, x and x plus a become to close, then their fraction is essentially 1, or that x plus a can be approximated by x. Again, you may say, so what? Let's put this is in real world example. Let's say I have $1 million and 58 cents. If I ask anyone how much money I got, they would say, you have $1 billion. Why is that? Because we say that, no. 48 cents are such a small mortgage. There's not big much of a difference. This is telling the same thing that math above 6. If it is then is a plus number compared at the 18 cents, then we can essentially learn x plus a at $1 billion and 48 cents. Basically, is a billion, $1 billion. The significant application of infinity limits is that it allows us to extensive complex functions and figure out which phase of information contribute the most to the answer. This will enable use to simplify problems to the point we can solve them. Rounding is the everyday applications of infinite limits and has significant applications in mathematics. Okay, so I think that's enough for me. And I will give some cues because your time is limited. So that was it living someone else's life. Stay choose. You know what I say? You know what I'm talking about. Okay. So this video. And bye.